Starting off the stream here. And let me start my screen share. All right, can you see my screen?
No.
Oh, not yet. Wait. Screen share. There we go. How about now?
Yeah.
Excellent. Let's see. Oh, should auto hide. Why doesn't it auto hide? Hide from hide floating panel. Hide names, breakout meeting. I don't know. I thought it was auto, this would auto hide out of the way. All right. Let's see. Let me close that. No form, do definition, relational. Great. Okay. All right. Let's give everybody a minute. Get started. Hello, Josh. Hi, Dua. Welcome. Welcome, Christopher. Welcome, Emily.
Hello.
Hey, Mike. How you doing? All right. All right. Let's get started. All right. Let's see. We are finishing up week number 3. We have gone and we have installed a running database, a relational database, MySQL, and it's a client workbench. We've also worked on a design database all last week. We talked about using UML class diagrams, lots of rectangles and lines and stars and numbers to represent the data in a graphical representation. And so today, this week, we've focused mostly on how is that we can implement that database, right? How can we convert those nice graphical representations in UML, how do we convert that into something more concrete into a database using the create statement, right? The SQL create statement. So we're going to continue talking about that today, and then next week we'll start talking about how is it that we can retrieve data. Actually, we'll probably get started today. We'll start talking about how is it that we can retrieve data from the database that we've created. Okay, so we'll finish up normal forms. I believe there were a couple of slides that we have to finish there. We're going to revisit data definition a bit, and then we'll introduce relational algebra. The assignment, the DB3 was we introduced it earlier this week, and we demo it. Right, we went and created a couple of tables for you. We walked you through how to do that, and it is and then we ask you to try and do it on your own. Right, we ask you how to, we implement for you a table. We create a one-to-many, many-to-many, and then ask you to go ahead and practice it on your own in the assignments. There's also a quiz out today. Came out early this morning, and it will be available till tomorrow at midnight, and it's about 30 minutes, and it's I think it's got four questions, maybe five questions maybe, and so they're all about UML, right, and design the database. So make sure you know your one-to-many diagrams, your many-to-many diagrams, right? That things such as inheritance, aggregation, composition, how to annotate it one-to-many and the star. So make sure you understand those things. Obviously, it's open book, and obviously you're required to do this on your own. So I'm going to post here my phone number if you need to, for some reason, an emergency. Feel free to give me a call. 5742. Please do not give this phone out. It is my personal phone number. But if you are in an emergency, please don't hesitate to reach out to me. If you do run into an issue in the quiz, maybe you don't understand something, or there was something misspelled, or something was wrong, take a snapshot of the question. Don't share it with anybody, and you can send me a private post on Piazza, or I'm actually going to create a post so that folks can reply to that with any issues you might have had with the quiz. But the answers are not going to be available up until tomorrow at midnight. The answer will be released after that, so you can check your grade while you lost points or not. Okay. All right, so let's move on. Any questions before we get started? All right, let's see. Let's finish up normal forms. Let's see real quick. The intent of normalizing a database, right? We say that we want our database to be normalized databases, right? But basically that means is that we have removed from our database the structure, how we organize the data. We have structured it in such a way that if we're going to store something, it's only going to be stored once. All right, it's not like we're going to have the same information in multiple places, right? If it's only stored once, we can guarantee that information, it is what it is, right? But not that we have two competing versions of the data that logically should be the same, but we have no way to enforce them to be the same, right? And because we can't enforce them to be the same, they could inadvertently, over time, right, have discrepancies. Where, for instance, in this one big table, we're capturing the fact that the professor is Dan, right? And so this value that is being repeated over and over and over, we have no way to enforce that this value is indeed always the same, right? Because logically, it's that professor. It means that one professor, right? So some ways that we could enforce this would be if we have maybe another table that stores all the professors, and then these would be maybe foreign keys, right? So there would be no way for us to mistype that this is Daniel, right? Because probably it's not a valid primary key in that other table, right? So that would be one way to enforce it. Yes. But if this is just a plain field, just a normal field, okay, there would be no way for us to enforce that this should be a specific value, okay, and that logically these would have to be the same. Yes. So to enforce it, we have to look for ways that we can enforce integrity of the data, right? And usually it entails adding additional tables. Right? For instance, here we could have an additional table that has a primary key of all the professors, and this would be foreign keys to those tables, right? And that's how you can enforce it, right? But if you don't enforce it, then we say that the database is not normalized, right? That somebody could have here and mistype this and put an O there, and we would not even know it, right? So if we ask about certain professors or whatnot, right? If we ask it one way, it might come back as Dan, or if we ask in another way, some other query, it might come back as Don, right? And that would not be good. Okay, so the way we fix that is that we split it, right? We split it in such a way that we cannot have the data represented twice, that it could introduce redundancy and inconsistency. All right, so we introduce a couple of type of problems. We introduce the first normal form, we introduce second normal form, and then we introduce, and then we'll introduce today third normal form, the last one. Okay, these all deal with different versions of problems that you could run into and how to fix it. Okay, the first one was we were looking at cases where we wanted to store information in a field that might have been designed to just hold one value. Okay, we looked at different versions of this. Look at this version, right? Then a separate column, that was no good either, or a separate record, that was no good either. And we had come to the conclusion that the best way to represent this was to have a separate table where we have the telephones on one end, and then we have foreign keys that reference the record that this phone is for. Okay. You seem to be cutting out a little again. Just a heads up. Thank you. Yeah, I guess maybe I'm gonna have to find a different place to do this. Just bear with me. Just let me know. And the next time, I guess I'll be somewhere else. Let's see, chat. Will do. Thank you. All right. So then we looked at a different type of problem, right? Where we were looking at some fields, right, that were depending on only half of the primary key, right? So second normal form deals with cases where we are considering composite keys, right, or primary keys that are made up of multiple fields, right? So let's look at examples here, and let's look at seats here, right? Now seats here, notice that for CS1500, right, for this semester, the value is 100. And for a different combination of course and semester, we have a different value. This totally makes sense, right? That this is allowed, that this value would be something for one combination, and it would be something else for a different combination, right? For the same course, Now let's look at this one over here for the course name. Now here, notice that the programming is the name of the course. But irrespective of what the semester is, it's always the same name of the course. It would make no sense, right, that for the same course, for a different combination of semester, that the course would be something different. Yes? So just like this makes sense for this to be one single value, CS1500, this would also have to be the same value for the same course. So basically, we know that this value is dependent on this course, on this part of the field, but it does not have any dependency between the semester. It's independent of the semester, right? Regardless of what the semester is, the name of the course is always the same. It's only dependent on the course ID. It would make no sense for this to have two different values, right? Or misspelled or whatever, right? Whereas this field makes total sense for the values to be different. This makes no sense for these to be different, okay? So here, we don't care of enforcing these values to be different or the same or whatever. But here we do care, right? Here we would want to enforce the case that these values are the same, right, across two records. But we have no way to enforce that. We have no mechanism to enforce it, right? Well, actually we do. What we do is that we normalize the table, okay? We say that this table is not normalized because it's breaking second normal form, where one field, a non-key field, meaning it's not a foreign key, it's not a primary key, it's a regular field, is dependent on a partial part of the key. It doesn't depend on the whole key, right? So it's breaking normal form, second normal form, right? So the way we fix it is that we make use of foreign key, primary key, right? We move all the data into one place where you have the course depending on only the key, right? This field here only depends on this primary key over here, which is perfect, right? It follows first normal form. It depends on the key, and now the seats depend on the whole key. Yeah, the seats depend on the whole key, right? So this matches first normal form. This matches second normal form, and the whole thing is now good, right? It's we don't have any breaks of the normal forms, okay? And the way these are related to one another is that this is a foreign key to this primary key over here, which makes total sense. All right, let's make another example. Here we have Alice, right? That has a combination of skills, and we have Cambridge. Now, logically, if one person can be only in one place at any one time, right? But we have no way, right? Notice that it would make no sense to Acton, right? That Alice would have 2 current locations. It would make no sense. But because this is not a foreign key or primary key or anything, there's no way for us to validate this or be notified that somebody put a value that makes no sense with the other values in there, right? This must have been done inadvertently by mistake, right? And it would be introducing inconsistency in the data, right? So because logically this value should all be the same because it depends on the person, Alice, right? So the way we fix it is, again, we introduce another table where we capture the location is now dependent on that one person, first normal form. It only depends on the primary key. Let's see a question in the chat. Why employee and skill is a primary key rather than only employee? Oh, because we're trying to introduce the idea of second normal forms, and second normal form is a specific for combination of skills. Compound keys, where you have a combination of fields that make one primary key, right? Otherwise, we would be talking about first normal form. We wouldn't be talking about second normal form, right? So yeah, the way we fix it is that we break it up into multiple tables, right? And there it is. This is your solution. The current location only depends on the primary key of employee, and this is not only a primary key here; it's also a foreign key to the other table. Okay, so let's look at this example. This example meets first normal form, meets second normal form, so it does not break either one, first or second, but it has a problem, and which is going to be a segue into the next normal form, the third normal form. Let's look at this piece of information. Let's see. We have Alice here. That it's a professor. Alice is teaching web dev in 2012, but in 2013 Bob was teaching web dev. See that? And it's okay, right? You can have different professors teaching web dev at different times. And same thing with Bob Marley was teaching Intro to Web Database in 2012, but then it was Alice who was teaching Intro to DB. Okay, so it's fine, right? It's we have this information which is dependent on both keys. It is okay for this value to be different for a different combination of the combination of primary keys. Yes. Well, look at this data over here. This birth, the date of birth, right? So this date of birth. Notice that this date of birth is dependent on who? Is dependent on the professor. This is the professor's date of birth, right? So it's dependent on another field where this field is neither a foreign key nor a primary key, right? So you have a dependency between fields, okay? Later on, next week, we're going to call this a functional dependency, right? There's a dependency between one field and another field, okay? And that's a problem, right? Because we have no way to enforce that these values are the correct ones, right? Logically, for Alice and Alice here, these date of birth should be the same, right? It would make no sense for this to say 1866 and this one 1865. It would make absolutely no sense. Oh, so so it's teaching web dev in 1866. Let's make this a little more realistic. So 1996, and teaching databases born in 1945. Maybe it was it got older to have databases at some point to teach it. Anyway, yeah. So it would make no sense. There's no way for us to enforce the fact that these has to be logically the same. If somebody types in the wrong date, right? There's no way for the database to let us know, hey, something's wrong here, right? There's some inconsistency, right? So the way to fix it, right? Always what we're going to do is that we're going to split it, right? We're going to split it. Where is it? We split it into a separate table where we capture the professor information in one table, and then we link them together, right, with this perhaps being a foreign key that references the professor over here. Okay, and now we have the information only once. right? If we make it wrong, if we type it here wrong, well, okay, we typed the wrong information, but at least it's not inconsistent, right? We would be consistent in our being wrong. Okay, so yeah, so the process of identifying that there's a dependency between fields, right, is, and then fixing it, is called third normal form. When a field depends on another field, we say that it breaks third normal form. Okay, and the way to remember this is that first normal form, we're saying that the fields, all the fields should depend on the key. The way to remember second normal form is that the fields should whole key, just like this guy, right? These professors depend on the whole key. And third normal form, we have to identify that it depends on nothing but the key. Like over here, this professor date is depending on the professor, is not depending on the key, right? So we have to, the mantra that we're going to try and drill into you is that the field should depend on the key, the whole key, and nothing but the key, right? Let's see on the chat. How is this different from, yeah, no, this is depending on fields, depending on each other, right? We weren't adding elements in the same field or adding new records to capture the same information. Okay, so yeah, so that's third normal form. We split again. All these, the solution is always to split, right? We split it in such a way that we now are fixing either third, second, or third normal form. Okay. All right. Let's move on. Okay, so yeah, so we had already covered data definition. I just wanted to review a couple things before we move on. So I moved a couple of slides here that I wanted to review with you. This is material that we already covered. I just want to make sure that we have full understanding. And also, there's some differences on how you do it in MySQL and how you do it with SQL Server or how you do it with Oracle. I just want to, I mean, you don't have to know, Oracle or SQL Server. We're fully focusing on MySQL, but I did want to make you aware that, depending on which vendor you're using, it might be slightly different. And it's up to you to make sure that you understand what the actual syntax of what you're going to be using. So let's talk about constraints. So what we mean by constraints, right? When we say that the database, we can enforce certain constraints, we mean that the database can work with us to validate certain things. For instance, if we declare fields to be integers, dates, strings, or whatnot, right? We are asking the database to validate and make sure that, right? If we say if we say it's an integer, make sure that folks are not inserting characters, right? Alphanumeric characters, right? In third normal form, does a professor field become the primary key of the new table? It could be a foreign key. Yes, it could be a foreign key that if we never had a professor table, but yes, if we split it, we would have a professor table that would have other things in there as well, not only just a professor, but maybe their office, where they're tenured, and that would be a primary key. And then the professor in the other tables would be a foreign key that points to that professor table. Yes. So yeah, so there's several constraints that we can ask the database to enforce to help us validate certain things. Like, for instance, whether it's an integer, a float, a date. Okay. And so let's go over some of the constraints. So obviously the data type. So let's actually put here, the field's data type. It's obviously a constraint. But there's some keywords that we use for establishing some more rigorous constraints. Like, for instance, not null, right? Which allows us to establish that this field is required, meaning, if somebody tries to insert some record into a database and that field doesn't have a value, don't let it go in there. Like, for instance, if it's a username, a password, or something that has to have a value. If your login screen or a register screen, right? We can't let you go through until you give us the minimum that we require, right? So you would enforce that by providing a not null. Unique enforces that if we're going to insert certain fields into records, right? We want to make sure that the database validates that the values. Okay, so I'll repeat not null, right? So not null. Here, what we're trying to do here, not null, is we want to make sure that we enforce that certain fields are required, right? That if somebody is going to insert data into a record that and that a field doesn't have a value, that we stop them. It says, well, no, there's certain records, certain fields like username, password that have to have a value. Otherwise, I'm not going to let you through in the user interface, and I'm not going to let you go through also in the database. Okay. Other constraints are, for instance, unique. We might want certain fields to be unique, right? For instance, it might make no sense to folks to have the same email, right? So we might label our emails to be unique, right? Even though that might not be the way we log in, we might have a unique username, we might have a unique email, right? We might have a unique phone number, and we want to enforce the fact that certain things make sense and certain things make no sense. It doesn't matter if I have the primary key constraint under the constraint keyword. No, it's good that you did that. Yeah, you could do that. Yeah, definitely could do that. We will see that constraint allows us to name the constraint, and we'll see that in a minute. And naming them allows us to at some point be able to alter them or manipulate them later on. So yeah, unique. Then primary key is kind of primary key is it's kind of like a combination between unique and not null, right? So primary key says, well, you have to be unique, obviously. You have to be not null. It's required. You can't insert a record unless I have a value for the primary key. But it adds additional constraints, right? It adds what we refer to as referential integrity, right? And what we mean by that is that these two work together, right? We have a record being a foreign key that is referencing another record over there that has a primary key, right? And this establishes a relationship between the two that by default, right? The default behavior is that if you try to remove a record that with a primary key that has another record that is referring to that primary key, the database is going to stop you. It's going to say, no, you can't remove, right? You can't remove a record if you have a whole bunch of other records that are referencing it, right? If I let you remove it, all these records are going to be left alone, or is going to be left orphaned, right? So that's the additional constraints, right? That primary keys and foreign key add to the mix. Let's see on the chat. Could you make it? Yes, certainly, right? We had said that that's the default behavior. It stops you, doesn't let you remove them. But you can override that with cascade, right? And say that, well, I'm not going to stop you. Instead, if you remove that record over there, I want that action to cascade to me, right? If you delete over there, then I want to delete also all these other records, right? If you change the value over there from 10 to 20, that has to propagate down to the other records. They need to be all changed from 10 to 20, okay? Or I can change it to ignore, because I don't care. If you change it, if you delete it, I don't care. I'll just orphan these records, and it doesn't matter to me. Let's see in the chat. So cascade works as if the parent is deleted, children are deleted as well. Exactly, yes. Which allows us to implement things such as either composition or aggregation, right? In composition, in UML, the way you implement composition in SQL is that you do a cascade, and it cascades delete all the parents, delete all the children. But aggregation, you would it would be a reference, right? But the deletion of one would not cascade to the other. Other things that you can do is default. A default allows us to say what happens if somebody doesn't provide a value, right? Even if it's required or not, right? If I don't provide a value, I can always come up with a default value, right? Maybe a default role when you are registered, right? a default date. So now
Professor?
the keyword for not null, yes.
You just cut out. I'm sorry.
Oh yeah, sorry. Could you repeat? Check. Yeah. Sorry about that. Yeah, I need to find a new place. Sorry about that. So actually, let me move elsewhere. See if it's better.
Thank you. I'm sorry.
Oh yeah, no, please let me know. Let's see if this is any better. Let's see if internet's any better here. Yeah, so check allows us to validate. Actually, no, I don't think I had described check. let's talk about check. So check allows us to provide like a regular expression to validate whether the data that you're inserting meets a particular pattern. Like for instance, if you have a zip code, you might want to say zip codes have to have 5 characters, right? Or 5 integer values, 5 digits. Or it might have 5 digits followed by a dash and followed by 4 digits, right? So check allow you to do that in your regular expressions. Also, it allows you to validate that a value, that a number is not negative, or it's within a particular range, right? So check allows you to specify those kind of expressions. And default already explained default. Yeah, so not null. The syntax is very simple. Not null. In MySQL, unique, like primary key, like foreign key, unique. The syntax is to have its own, in a separate line, you say, which field is unique, right? Like this PID is unique. In other servers like Oracle and SQL Server, right, the syntax is slightly different. You can put the keyword right on the field. Okay, so again, whenever you're going to use a specific database vendor, right, you have to be familiarize yourself with the specific syntax of that vendor. Okay, but you're not going to be responsible of knowing SQL Server or Oracle unless you are already. And if you use that syntax, let me know, and then we can we can use that as well. As I mentioned earlier, you can name your constraints. You don't have to, but you can, and it's oftentimes a good idea. So if you ever want to be able to modify these constraints later, right, with the alter command. Remember we showed you the alter command in one of the assignments. You can alter the table, right, and the way you alter it, you can refer to the names that you have created here in the constraints, right? So you can put the unique all by itself, or you can put the unique and then name it. You can name the constraint right in front of it. Okay. Now these names need to be unique. Primary keys in MySQL, primary key, like we've seen so far, you have it has a separate line. You can say primary key and then which field is the primary key. But in Oracle and SQL Server, the syntax is slightly different. You can put primary key right on the field when you're declaring it. Okay, so slightly different. Now we did mention that you can have composite keys, and we never covered the syntax to do that, right? So composite keys, you can create them using parentheses, right? And then using a comma separated list of all the fields that combined need to be unique. So PID by itself doesn't need to be unique. Last name by itself doesn't need to be unique, but the combination of PID and last name need to be unique. Okay, and here is we're optionally, you don't have to you can optionally name the constraint so you can refer to it later. Foreign keys. Foreign keys we saw earlier, right? It's just a foreign key. You're saying that this PID is a foreign key referring to some other field in some other table, and that's the field that is referred to in the other table. SQL and Oracle is slightly different, right? PID and you can put the foreign key declaration right when you were declaring the field, so slightly different. And you can name the foreign key. You can name it the constraint so that you can change it later if you need to change it later with alter. So if you are referring to a primary key, right, like over here, we had a primary key that was a composite key, right? So here's a table that declares a combination of fields that need to be unique. You can refer to them in the foreign key. You can say foreign key and say that you're going to have two fields, right, in this table that are going to refer to two fields in some other table, right? So here you're saying that, hey, these two local fields, these two here, right, are going to refer to some other two fields in some other table, okay? And so this is how you establish that. And default, we looked at that already. Auto increment, we saw that already, that it starts with increments at 1, 2, 3. Some databases will start at 10, 20, 30. Different vendors behave differently. Let's say it's a question on the chat. Is that a composite foreign key? Yep, a composite foreign key, exactly. This one over here, right? It's a composite foreign key, yep. Meaning it's referring to a composite primary key. Yep. Where are we? Okay, auto increment. Now in wait a minute, default dates or increment. I think I should put this here. In MySQL, auto increment is to auto increment like we've done in the assignments. But in SQL Server, we use the identity keyword. The identity keyword. Let me put the default here. Defaults, yeah, two defaults here. Default, the dates. We could use current date time. But I did want to point out these two, right? Auto increment and identity, slightly different in SQL Server. Now, to insert data into these identity or auto increment, the syntax is slightly. There's two different syntax. We're going to cover this in more detail next week when we talk about inserts, updates, and deletes. But just a small peek of what's coming is that when you insert data into a table that has a primary key, which is auto increment, there's two ways that you can treat that. One way is that when you insert, right, you only insert the fields for which you have data, and you don't even include the primary key here, right? And you just leave it out, and that's fine. What's going to happen is that when the database is going to look at that record, it's going to create a brand new primary key for it, and it's going to use that value. Now, there's another syntax where you can insert records, right, without the field names, without the column names. Like, for instance, you can just provide values. And here, it uses the order of the fields to know what values are this for, right? So, for instance, if the primary key was declared first, then this would be for the primary key. This would be for the first name, and this would be for the last name if they were declared in that order. So what do you do with a primary key that has been declared auto increment? Well, what you would do is that you would leave out the value by saying null, right? You would not do this, for instance, right? This would be a mistake because primary key, it would assume that this is the value for the primary key. It's expecting an integer, and it's going to fail, right? So we need to. You can't just skip over. This has to be in the order as the fields were declared. Okay. And finally, you have the way that Oracle is implemented is you have sequences. Instead of auto increment, you have sequences that you can create very large collections of unique values, right, from which you can then pick out the next value. Okay. All right. I just wanted to make sure I covered that. Will the mistake execute on the application? It will stop, right? It will not continue. Yep. Hold on a second. All right. Okay, so let's move on. Let's now move on to relational algebra. All right, so up to this point, right? Up to this point, we have been spending most of the time talking about the structure of the data that we are going to be storing, right? And what the relationship is, and normalization, and how is it that we're going to create the database. And out of curiosity, what would happen if two people have the same name? The primary key would be the same in that case. Of course, yeah, one would fail. The second one would not let you introduce something that has the same value twice. Yep. And you would have to notify the person. Probably the problem is that you chose a wrong primary key, right? It was a failure in the design as opposed to a failure people inserting data. Yeah, so we've spent the last 2-3 weeks talking about how to build a database, right? How to create the tables and all that. And so we're going to start talking about in the next 3-4 weeks. We're going to start talking about how do we retrieve the data? How do we get it back from the data that we've stored in the database? Okay. Now, a lot of research went into this question, even before there were any databases that ever existed. And so Edgar Codd was, in the 70s, he established all the mathematical foundation on what today we take for granted as a SQL and relational databases. Okay, and just like early, before there were any computers, a lot of the mathematical foundation was established. Lambda calculus and all that was established even before there were any computers, right? So these folks were thinking, once we have these databases, how are we going to interact with them? How are we going to retrieve data? What are the challenges that we're going to be facing? Okay. What Edgar came up with was a set of operations that we can use to retrieve data from the databases, right? They envisioned data being stored in rows inside of tables, right? And then that could be treated as if they were kind of like data sets, and we can apply a lot of the ideas of set theory, right? Of unions, intersection, and all those operations. We can borrow a lot of those ideas to implement retrieval of data in relational databases, right? So one of the operations. So we're going to first look at operations that apply to single tables, and then we're going to look at operations that apply to two tables. Okay, so let's look at first one table. So again, the way this was envisioned was that data sets were going to be records or rows in tables, right? And these might be thousands of records in one single table. There might be 10, 20, 30, 40,000 records in one single table. And what select does is allows you to extract a subset of those records. Out of the 40,000 records, you might say, well, I only want to look at 1,000 of those records. Okay. Now, project allows you to decide. So select allows you to filter and say, I only want something that is this big. I only want a smaller subset. Whereas project, right, as records come in, each record might have multiple fields. And so what project allows you to do is says, well, each record might have 20, 30 fields, but you might only just want a subset. I might only want 2 or 3 fields out of those 20 fields, right? Sort does exactly what it says. It allows you to not reorder the data, but order it so that we can view it in a specific order, right? That maybe by date or by last name or by phone number, right? We might order it and take a look at it for view, mostly for viewing purposes, right? It doesn't actually reorder the data in the database. Then we have a rename. Rename, like the name suggests, allows you to rename fields or columns that's going to become very handy later on when we do self joins and other operations, or when you want to make a union between two tables into one single table. So that's definitely going to be useful there. Extend allows you to calculate new fields on the fly, right? So fields that that can be a combination of other fields, right, that you might not want to store in the database. So for instance, right, if you have a first name and last name, a field that might be useful is to calculate the full name, right? The full name would be the concatenation of first name and last name, right? And you would not want to store a full name in the database because that would break third normal form, right? You have a full name that is dependent on two other fields, the first and the last. So that's breaking third normal form. So one way to get around that is that you don't actually create the field. You can calculate that on the fly when you're retrieving data from the database, okay? Group by allows you to consider multiple records and group them together, right? Say that we have employees that might be in the same project or folks that are in the same section, right? And you want to combine them and collate them, right? Maybe apply some aggregation that you want to add them, you want to average them out, right? It allows you to group them together and then treat it as one single thing in one single group. Okay. All right, so these are all operations with a single table. And now these operations meaning single table, meaning that as you're operating on them, they're going to have to iterate over all the records in that one table, right? And as they're iterating, right, they're going to do these things, right? They're going to filter, they're going to extend, calculate something new, or treat them and identify which ones are in the same group. Now, there are two table operations. They take, like the name suggests, right? They take two tables, right? And then combine them somehow, right? The first combination is the product combination. So the product combination is basically you're taking two sets, right? And then calculating what are all the possible combinations between those two sets, right? So say one set you have, A, B, C, and the other set has X, Y, Z. Well, all the combinations would be, A combined with X, Y, Z, then B combined with X, Y, Z, and then C combined with X, Y, Z. Notice that to calculate this, right, if you're going to iterate, if you want to implement this in a programming language, you would need two loops, right? You would need an outer loop that loops over ABC, and then for each one of them, you need to have like an inner loop that iterates over XYZ, right? So something that was time complexity of linear time complexity. I don't know if you folks have taken algorithms or one of these other foundational courses, right? If you have only one loop, right, we say that it's order n, right? It's linear. But if you have two loops, one instead of the other, right, it becomes quadratic, right? Because if you have one size n and the other one size n, you're going to have n times steps, to iterate over all the possible combinations, right? So it becomes much more expensive, right, to consider all the possible combinations. So we have to try and see if we can avoid them somehow, right? Now, some of those relationships, some of those combinations might make sense, and some combinations might not make sense, right? And we might want to filter out which ones make sense, right? So, for instance, we might say, well, we know A is related to X, Y, but not Z, and B is related to Y, Z, but not X, right? So we might want to know, yes, I want to know all the combinations, right? But I want to filter out and only keep the ones that make sense to me, right? The ones that are actually related. Then you have semi-joins that allow you to match things that you might want to, when you do a join, right? When you do a product or a join, you're bringing data from both tables, right? Data from one of the tables, you bring all the columns and all the rows from one table, and then you bring all the columns and the rows from another table, okay? And sometimes you don't want to do that. Sometimes you just want to know that A is related to X, Y, and that's it, right? You just want to know that A has a relationship, and so I want to know the X, Y. It says, do X, Y have a relationship over here? Yes, they're related to A. Okay, well then I want X, Y. I don't want A. I just want to know that there was a relationship. Okay, so semi-join allows you to do that. You find which ones match between the two tables. Then you have anti-join. Anti-join is kind of like the opposite of join. Join identifies kind of like the intersection between two sets. Which ones are related to one another, the intersection. Right, which ones match? Anti-join is like the opposite. It finds the records that don't match. I want to know the ones that don't match, right? So anti-join is for that. Union allows us to take data from one table, data from another table, and then just like concatenate them, right, and make them into one bigger set. And outer join allows us to find data, the whole data, right, even the ones that don't match, right, the ones that match and the ones that don't match, but in a specific set of combinations. Let's see, chat. When you say match, do you mean related? Yes, related. Yeah, related, that there's a field in one of the records that matches a field in some other table. And to join, would the tables need to share a common column to join? Yes, yes. In our case, it would be foreign key, primary key, right? That we know that the foreign keys are referencing something in the primary key. Yep. Yes, but right now, we haven't introduced the, we haven't yet introduced the fact of primary key, foreign key. We're just saying that one field in one of the tables has some relationship with another field in some other table, which obviously we know we implement using foreign keys and primary key. Can I think this in the Venn diagram? Yes, exactly. And we will use the Venn diagrams in a second or in a few minutes. Okay, so let's start using some of these. Let's look at some queries. So here's a query that you might want to execute on a table, the outer join. All right, so yeah, when we get to the outer join, I'll talk about the outer join in more detail, because there's also left join and there's right join. So I want to talk about the whole thing a little later. So here we have the select, and the command would allow you to answer questions such as this, right? So what are all the students who graduated in 2004? Okay, and so presumably you might have a table called students that allows you to, that has all the students in there, and we want to retrieve from the students those students that meet a particular criteria, right? So this might be select, takes two arguments: the actual table from which you are extracting the data, and then a predicate, saying, well, which ones do you want? You want to filter out. You don't want all the students, not all 40,000 students, right? Which ones do you want, right? Well, the ones that meet that criteria. And this is syntax, right? So this is the functional syntax, right? A function that takes two arguments. So here's a predicate, and here's the table from which we're filtering. Now, mathematically, we document it this way, right? We use the letter sigma to specify select, right? It takes the table as a function, and then down below, under the right next to the sigma, we put the actual predicate. Okay, so here's a couple examples. Students who graduated in 2004 with a major of 10 or 20. So look at this or. So or, this is somewhat suggesting that we have Boolean expressions, right? That that you can combine these by making much more complex Boolean expressions by combining them with ands and ors, right? So here it is. So we can take the predicate, right, and use and or to combine that. You want the major IDs either 10 or 20, and of those, I want the ones that are 2004. Okay, all on the students, right? And here's mathematically with using the sigma format, right? We have the and operation here, right here. Okay. Now we can also nest queries where the output of one query can be the input of another query, right? So for instance, here, the same exact question that we had earlier that we're trying to implement, this one right here, the same question, we can implement it in another way, right? We can have an inner select, right, that first filters by the graduation year, and that could be the output of this query can then be the input of an outer query, right, which then filters by major ID. See that? Now we're going to be also introducing this nomenclature where we are assigning the results, right, of a query. We're going to assign it to a variable, and that variable is going to be treated. We can treat that variable as if it were a table, right? Because the student is what? Student is basically a collection of records. Well, the result of the select is also a collection of records, right? Those records extracted from students that meet this criteria. Okay, so we're going to assign all those records to a variable, and that variable we're going to be able to treat it as if it were a table, not a real table. Later on, we're going to refer to them as virtual tables. We're going to refer to them as views, right? We're going to be spending some time talking about this a little later, okay? But for now, let's refer to it as just a variable that is receiving the subset of records, right? So it's a collection of records that can be treated as a table, right? So here it is. Here's an example where we are retrieving all the students in graduation year 2004. We're assigning it to Q1, and then Q1, we're then using it, right, as an input to another select statement, right, which is retrieving those students that by major ID. Okay. Now we can also represent it graphically, right, by using this flow diagram where we have the table from where we're extracting, the filter that we're applying, and then other filters that subsequently make the data much more specific to what we're looking for. Okay. All right, so let's talk about project. So project, as I mentioned earlier, it shrinks the result sets horizontally, right? So if select filters vertically, then project filters horizontally, right? I only want a subset of the fields. I don't want all the fields, right? So if you give me a set of records, I'm only going to give you back certain columns. So if you might 10, 20 columns, what project does, it gives you the same exact table, but with some missing table columns, right? It removes certain. So select removes rows, whereas project removes columns. Okay, so together the select and the project, right, work together by removing columns, removing rows, right, and giving you exactly what you want. Okay. So here's a student, and we're only keeping these two columns, and we're dropping the major ID, we're dropping student ID, we're only keeping those two. And the nomenclature here is that it uses the pi symbol to represent project. Now we can combine together the project and the select, right? That the select can be used to filter, right, vertically the records that you want, right? And then once you have identified a subset of those records, you can then squeeze, right, and only keep those fields that you want, right? And we can represent it functionally this way, right? Or you can use it graphically this way, right? Where you have the student and then filtering out using different criteria, and then the field or column that we want to keep, or we can also specify this other way. Now we have to be careful that depending on how we do the queries, we might end up with no results whatsoever, right? It could be that the inner query might come back with something that the outer query can't do anything with it, right? For instance, this one over here is looking at the student table, right? It returns in the entire set of records, but only the student name, right? And so now you have only one column, and that's going to be used as for the select, right? And the select is going to try and match against the major ID, but there's no major ID. It's gone, right? Because it was removed, right? I'm only left with the student name, right? So this would come back with an empty query, right? It would just not come back with anything. So it's a meaningless query. So we have to be careful. Sorting, like the name suggests, it allows you to reorder only for viewing purposes, right? It's not like it's actually going and moving any rows around, right? It's only for for viewing for us users that we want to sort it alphabetically, or we want it numerically or whatnot, right? And you can give it the table or the data set, right? And then it will order it first by one field and then by another field. Renaming allows you to take a column in one query or result set or table and rename a field in that table, rename it to give it a different name, right? It's very useful for like unions or for doing self joins, which we'll see in a minute. Extend allows you to calculate fields on the fly, right? That, for instance, here, we're looking at the student table that has maybe 4 fields, and we're going to generate a 5th field, and we're going to call it graduation class, right? And all the values are going to be calculated on the fly, right? So as it's iterating over all the records, it's going to take the values from the records that it's in, right? And it's going to calculate, do whatever expression you want to put in here, and that's going to be the values for that record. These are not data. This is not data that's being inserted in the database, right? This is not affecting the original table, right? This is only creating data on the fly, right? That you can use later for other queries and post processing. Okay, so let's look at group by. So group by is fairly complex, so bear with me. But the idea is that group by allows you to identify, if you look at the data in a table, right? Some of those fields are going to have values that repeat, right? So for instance, if we are students in the same section, right? I'm going to have the same section as you do, right? And there's going to be a lot of us that are in the same section, or we might all be in a particular project, right? We're all working here in this project, and those folks are working in a different project. And somebody might want to ask and says, well, let's group everybody by project, right? So I have 13 engineers working on this project, 20 engineers working on that other project, right? And then I can now treat all those engineers in that group. I can treat it as one single entity, right? A single group. And then I can specify what fields do I want to group by the project ID, right? By section ID, by whatever, right? And once I have you in one single group, right, I can apply some aggregations. I can say, well, what do I want to do? I want to know the budget for that project, right? Well, I'm going to add everybody's salary, right? And, well, you make 100,000, and here's 70,000, 50,000, right? So I can add up everybody's salary and know, well, how much money per year is being for that particular project, right? Or I can group all the quizzes, right, per student, right, and then calculate what the average is. So there's a lot of aggregate functions. There's sum, there's aggregate, there's count, there's max, there's min. There's a whole bunch of functions that can aggregate the values and calculate a single value out of the elements in a group. So let's take a look at an example. So let's take out the students, right? Students, there might be 40,000 students, right? And say there are, there are 40 majors, right, in the school, the different colleges and schools and whatnot. So that means that on average there might be 1,000 students per major, right? And then, so that means that I would end up with 40 groups. It would be 40 groups. Yep. Out of 40,000, I'm going to generate 40 distinct values, okay, in one per group. And what are the values? Well, whatever I use here for the aggregation. In here, I'm aggregating values in the student, and I'm calculating, for instance, the minimum graduation year and the maximum graduation year, right? So the output here is going to be the majors, right, which are going to be 40 of them, and then the values, the min and the max of the graduation year. So there's going to be 3 columns that come out of here, and there's going to be 40 rows, right? So here's an example, right? Here we have Joe, Max, and Lee, right, are in the major ID 10. See that? Whereas we have Amy, Sue, Kim, and Pat are in major ID 20. And then we have Bob and Art in major ID 30. See that? So basically we have, if we group by major ID, there's basically 3 distinct major IDs, 10, 20, and 30. There's 3 groups, right? So graphically, it will look something like this, right? You have group 10, group 20, and group 30, right? And now I can apply different aggregation functions to this, right? I can count the SIDs in each group. That would give me 3 here, it would give me 4 here, and it would give me 2. So it would be 3 distinct results, right? With 3, 4, and 2, if I'm using count. I can average these values. Now, does it make sense that I average SIDs? Probably not. Nevertheless, I can apply average. I can apply sum. So the sum would be 9 and 1, 10, 13, and then the sum of this, and then 12 here, right? I can do max. For instance, I can use max here for the graduation year. I can say, what's the maximum graduation year for group 10? It's 2005. What's the minimum? 2004. What's the maximum in this group? Well, it's 2005, and the minimum 2001. And for this, minimum 2003 and maximum 2004, right? So I can calculate all those averages, mins, max, sum, count. Okay, a question on the chat. Are there any rules for what order they're shown in? So no, there's no order. In SQL, there is no ordering, right? You cannot guarantee any order whatsoever. You can sort, right? You can apply a sort operation, right, which will order it any way you want, but the actual data in there is it has no order. Right. So the results of applying this would be this right here, right? The result would be you get the major ID, so the 3 different groups, the minimum, right, and the maximums, right? So this is the original data. This is the groups that were identified, and then these 3 will be collapsed into one single result. These 4 will be collapsed into one single result, and these 2 will collapse into one single result. And the results are, you know, the majors, right, the mins, and the max, right? You can also group by multiple fields, major IDs and graduation year. That means that whenever these match, right, you have 2 records, right, that have the same major ID and the same graduation year, then they will be considered in the same group. Like for instance, over here, if you look at this, this would now be a group, and this would be a different group, right? Because this has the same major ID and the same year, so that's one group, and this is a separate group. Now this would be another group, that one, then this is with another group, and then these 2 would be in another group, right? And this would be 2 distinct groups, right? Now, if we count for this group, how many there are? Well, there's 2. In here, there's 1. In here, there's 1, 1, 2, 1, and 1. Okay? And that's where you come up with something like this. 2, 1, 2, 1, 1, 1, 1, 1. Okay? After having counted them, right? And here graphically, you can see whatever they count. So because we use count, see that we're counting the SIDs in each group. And the reason we're counting the SIDs is because we know that the SIDs are not going to be null, right? That we don't have a problem of this somehow being null and we're getting the wrong number of counts, right? Now, if you group and you leave out the grouping field, meaning you're not saying that you're grouping by major, by project, by whatever, by section ID. If you just leave it out, right, as empty, then the default behavior is that it treats the whole table as if it were one big group. Okay, and so you can apply aggregations to the entire table, right? So that, for instance, you can count all the elements in one table, for instance, or you can, you know, how many rows are in one single table. You can count what is the min or the max in the whole table, right? So you can aggregate the entire table, or you can leave out the aggregation, right? And only put in the grouping fields, right? And what that will come out to be is you'll only get the, you know, all the distinct groups that you have in there. Okay. You can also all the aggregation functions have 2 versions. It has the regular ones that we've been using so far, and they have a distinct version, right? The distinct version, for instance, the difference would be if we were counting, for instance, graduation year, right? If we're counting how many there were per group, this would come out as 3 distinct 3 years. Would count as 3 years. This would count as 4, and this would count as 2, because there are 2 years in each one group, right? But instead, if you use distinct, this would count as 2 as opposed to 3, and this would count as 3 as opposed to 3 as opposed to 4, right? Because these are the same. So we want the distinct values. Okay, so we have distinct versions of that. And as I mentioned earlier, careful, right? If you have null values, they will not be counted. Okay, so careful if you count something that has null values, and you might be undercounting how many records you have. So it's very common to instead to always count on the primary keys, which is guaranteed not to be null. Okay. Use the combination of using grouping for answering a common question here. For instance, what if we want to calculate how many, what are the most number of A's of any section, right? So for instance, you can implement that question by first retrieving all the enrollments for which the students got an A, right? So that would give you this. For instance, you have there are two sections. Section 13, there was 1A, and in section 53, there were 2A. See that? Right. So that's this question right here. It gives you Q18. Now, if you use Q18 as an input to a group by, you can group by the section ID so that you can make 13 in one group and 53 another group, right? So group by these two, so there's two distinct groups. And then you can count the EIDs. How many are there in each group? Well, there would be 1 in this group of 13, and there would be 2 in the group of 53, right? So there's a Q19 would end up with this, right? The groups of the section, and then how many EIDs are there in each group. Then you can use that as an input to group by, again, group by nothing, meaning I want to take the entire table as if it were one thing, right? And I want to do the max, right? So what is the max of this? And it would come back as 2. Let's give you 2 over here. So yeah, so that allows you to calculate something on there. All right, so let's take a look at, so all those are one table operations. Let's consider now 2 table operations, right? So 2 table operations, like the name suggests, takes 2 tables, for instance, A and B, right? And there might be each one with records, A1, A2, and B1, B2. And so the product would be basically the combination, all possible combinations of records from one of the tables with records in another table, right? Let's see a question on the chat. Could you have done Q20 without group by? Q20. Well, you would need to count it, right? Well, no, in this case, max. I don't see how, but you can try and propose something. You need an aggregation, right? You need to aggregate, which can only be done with a group by. It could be an implicit group by, or it could be an explicit group by, which we'll see later when we look at how to implement this in SQL. All right, so product is the, all the combinations of implementing this. And remember that we're implementing it by having an outer loop and an inner loop, right? So this is quadratic time to do this, right? Here's an example of 2 tables, and we're only going to consider just a snippet of the table, right? So here, Joe, we're going to combine it with computer science. Joe, we're going to combine it with math, right? And Joe with drama, and then Amy with computer science, Amy with math, and then Amy with drama, and then Max with computer science, and then Max with math, and then Max with drama, and then Sue, and then Bob, and whatnot, right? All the possible combinations. And you would end up with something like this, right? But we're not doing the whole thing. We're only doing it with Joe, Amy, and Max, right? So you would end up a product would bring the records and the columns from both tables, right? And would combine them into one single big result set, right? That contains the columns and records from one table and the columns and records from another table, now as one thing, as a product, right? That's what it gives you. Now, we might not want all these, right? Because notice that we know, right, that Joe is really in computer science. Joe has nothing to do with math, has nothing to do with drama. We know Amy has nothing to do with computer science, but definitely has something to do with math and nothing to do with drama. So there's a lot of these that make no sense, right? The product computes all the possibilities, but typically we don't work with the product. Typically we work with a subset of the product, right? Which ones? Well, the ones that have something to do with the primary key equal to the foreign key, right? right? The Joe's is in the computer science, Amy in math, and Max in drama. So typically we don't work with product, we work with a combination of product and then filtering those that meet a particular criteria of some foreign key equal to some primary key. Now, this operation of combining product and select is so common and so useful, has its own name, join. Join, joining two tables, right? Takes two tables and then some predicate, which is basically it's syntactic sugar, right? It's an alias to a combination of a product and then a select on that product with a predicate, which is basically usually a foreign key equal to some primary key, right? Again, it's so useful that it gets its own name, right? It gets its own mathematical expression, right? Well, with the two tables and the predicate. All right. Now, if you consider it as a Venn diagram, the representation would be that you're looking for the intersection, right? I don't want all of them, all the combinations of table A and B, but I only want the ones that make sense, right? That have something in common. In this case, would be that some primary key is equal to some foreign key, which is the predicate that we're using to filter out and identify which ones match. Okay. Now here's an example of a join, right? That allows you to answer this kind of question, right? So grades that Joe received in his course during 2004. Okay, so well, first we know that Joe, the name of the student, is in the student table. We know that the grades are in the enrollment, and we know that a section, when it was offered, right, what year, is in the section table. So we need to join three tables, right? So, but the syntax is that we can join only two tables at a time, right? So here it is. So first we're going to retrieve those records whose name is Joe, in this case, just one record. And we're going to join that, and we're going to put that one record in Q25. Now we're going to join that, right, with the enrollments, right, so that we can find the enrollments for which the student ID foreign key in the enrollment table is equal to the student ID in the student records, right? So we want to know which are the enrollments for Joe. So this comes back here with the enrollments for Joe, right? On the other hand, we're going to start with the sections. We're going to filter out. We only want the sections of the year 2004, right? And put it in Q26. So these are the sections of 2004. Now we're going to grab both of these, Q26 and Q27. We're going to join them to. I'm going to say, well, I don't want all the sections. I don't want all the enrollments. I only want those enrollments for where the section was 2004, right? So we can take the enrollments for Joe, of which there would be some enrollments in 2005, 2006, right, or 2001, right? We only want to filter the ones in Joe and match them with those sections of 2004, right? And so this is going to come back with the enrollments, and we're going to come back with lots of columns, right? Columns that I got from student, columns that I got from the enrollment, columns that I got from the section. But here they were asking only for the grades. So we're going to use a project to filter out all those columns and only keep the grade column, right? Graphically, you can represent it this way, right? Where you start the student that gets joined with the enrollment, and your section gets, and that result gets joined with the section to give you the end result, okay? Here's another example, right, that we have, question in the chat. SID, ISIN, SID, ISIN, I don't know what SIE, I don't know what that means. Q25, correct? SID is in, yes, okay, SID, yes, correct, that is correct. Just another quick example before we leave. So we have here employee and department, right? And notice that they share the department here, right? So these are presumably a primary key, department primary key, of which the department here are referencing. I guess the arrows are backwards. I get the arrows backwards here. So let's see. Let's go the other way around. Yeah, there we go. Yeah, so these are all foreign keys. These are all foreign keys referencing these department here, the primary keys. And then we're joining these whenever they match, right? So finance matches with, there's 2 finance here, and we get 2 records, Harry and George, both in finance. And then we have sales here that match here, and then we have the sales Sally and Harriet. Notice fields from employee, and then fields from manager, from notice that production has no match. That's why we don't get it in the final results. Okay. All right. Okay, so I'm going to stop here because this is going to get fairly complex. We'll continue this on Tuesday. There any questions?
On that last part, just when you were explaining the arrows, you cut out just slightly. Can you repeat that again?
Yeah, no, I was saying that this was just another example of joining 2 tables, of which you have the primary key for the department being referenced by a foreign key in the department name by employee, saying that this employee is in this department and whatnot. And when you join them, right, you get 2 of these records match the finance, right, and that's these 2. So this, half of this information is coming from one table, and half of the other information is coming from the other table, right? So we're combining data, from 2 different tables into one result set, right? So Harry and Sally is these 2. And then Sally and Harriet, right, are these other 2. But notice that production, since no employee has a foreign key to production, this record doesn't make it into the final result set, right?
Thank you.
Yeah. All right. If you could look at these slides and look and finish them up, and so that when we come back on Tuesday, we can continue working on this. All right. I just want to double check that SID is in Q25. The SID is enrolled, correct? Yes, correct. Correct. Yep. All right, everyone. Thank you. Have a great weekend.
Thank you.
Thank you.